This is a combat robot weapon blade with integrated motor made from solid titanium, and it's designed to never stop spinning. In the previous video, I went over the design and manufacturing involved to bring it to life, but now it needs to go into a combat robot to put that theory to the test. So in this video, I'm going to show you how I used advanced 3D printing materials and unusual design choices to make this. My name is Angus, this is Maker's Muse, and this is Dead Cat Bounce. Let's get started. In the previous video, I talked about Nyant. This little vertical spinner was a ton of fun to compete with all those years ago, and it dished out its fair share of damage, but it had literally no armor, and with how competitive the Antweight class has become here in Australia, that's just not going to cut it anymore. This hub motor is the start of a whole new vertical spinner design, which I hope is as durable as it is destructive. But now comes the hard part. I need to design the rest of the robot around it to be just as tough, and we need to fit it all within the tiny 150 gram weight limit. For drives, I'm going to go with these N10 gear motors from Wranglebox. These motors are a premium option for Antweights, but they actually weigh less than the previous motors I used while having more power, and they're more compact, plus they have a steel faceplate, which should be much more resilient to impact. To control them as well as the weapon, once again I'm using a Malenki Nano. This combines the roles of several motor controllers as well as the receiver all in one compact board, which is super handy at this scale because it cuts down on a heap of wiring. The battery is this 2-cell 195 mAh pack from Llama Forge here in Australia, and the weapon system, well, you've seen it already. This massive hub motor is made out of a 1408 size brushless outrunner that's been carved up and inserted into a solid titanium blade, and it's controlled with a cheap 40 amp brushless speed controller running AM32 firmware. I actually don't know what these speed controllers are called, but they seem to work great, and we've just started calling them the No Fish ESCs because of this little icon on them. So it's time to fire up CAD and get to work. No, just kidding, you know the rules, it's pen and paper time. Always sketch out your ideas before launching into CAD because you can box yourself in to your knowledge of the software instead of exploring really creative ideas with pen and paper. And the best way to design Antweight robots by far, in my opinion, is to just lay out the parts on some grid paper and smash out some concepts. We've already got this big vertical chunky disc, so I just traced it and then figured out how to fit everything around it in a nice compact package. With a notebook sketch serving as my template, we can now finally fire up CAD, and this was my first pass. The huge blade in such a tiny frame looks pretty ridiculous, and I don't doubt it'll dish out the damage, but those wheels indeed do look pretty vulnerable. It wouldn't take much for another spinner to clip them at the front or rear and just tear them right off. The rear cavity does seem to have plenty of space for all the electronics, but again, it's also very vulnerable if my opponent gets a lucky hit to the back. Also, the blade actually extends down past the frame. This is intentional because the wheels will give the robot some clearance, but I'll definitely need some sort of skid to stop it from smashing on the floor as it drives around. Thankfully though, because it's so tiny, the frame weighs less than 20 grams so far, so there's definitely weight to spare for a bit of offensive design and a lot of defensive design. And I've got this absolutely wacky idea I've wanted to try for some time. A long time ago, I had a beetleweight robot called Fugu, and it was covered with these metal spikes made from bicycle spokes. The idea was that these spikes would soak spinner hits before they even got to the chassis, absorbing the energy and deflecting, or at worst, ripping them off like ablative armor. I want to apply that armor philosophy again here, but instead of using metal spikes, I want to try 3D printing flaps made from squishy, durable TPU. TPU has already proven itself as a wonder material for combat robots at this scale, and let me tell you, it can really take a beating, so I reckon something like this could work as lightweight armor. My hypothesis is that horizontal spinners will catch on the fins, and vertical spinners should be kept far away enough from the bot by them so they can't land massive hits on the other side of the chassis. And if they do get too damaged or ripped off, who cares? That's what they're there for. But what kind of TPU is best for this application, and what material should I use for the chassis itself? Ford AM were originally the sponsor for this video, and they provided all the materials I used for the build. But since finishing the video, they have now filed for insolvency, which was unexpected to say the least. The materials they provided did perform quite well, but I'll most likely be looking into alternatives in a future video now that things have changed so dramatically. It is what it is, and I wish the marketing and product management team over at Ford AM the best, but let's get back to the video. Starting with the TPU. From this super soft and elastic 85A shore hardness TPU to a more standard 95A TPU, which still has plenty of flex but a little less squish, I guess, all the way to this stuff, which I bet most of you didn't even know existed. This is TPU with a shore hardness of 64D. It is the hardest TPU you're likely to come across. It's still flexible, but it's actually quite springy, and I suspect it'll create incredibly tough 3D prints. From my experience, the softer a TPU is, the more resilient it is to impacts in the arena, but that comes at a cost of rigidity. For the weapon uprights of Dead Cat Bounce, a solid impact will force the weapon assembly down, and these uprights need to transfer that force through to the floor without deflecting or absorbing too much energy, which could suck all the power out of the hits, or worst case, bend the blade into the chassis, annihilating itself. On the other hand, the armor fins are purely there to deal with impacts, and they can deflect as much as they need to. Finally, there are the wheels, and I have this absolutely wacky idea for them. Because this robot's wheels are fully exposed, one good hit on a standard solid wheel would easily tear it off and probably bend and break the shaft on the expensive gear motors in the process. But if the wheels could absorb the impact or ablate away, like the rear armor, well, you know where I'm going with this. Enter the fin wheel. Okay, I know, this wheel looks like something you'd find on a moon rover and not a combat robot, but it was very intentionally designed to absorb and deflect direct impacts from weapons that would tear up a standard wheel. It's also been designed to actually be 3D printable out of very soft TPU. The wheel portion holds a foam tire, which is then protected by these ribs, which fan out radially from the central hub. When you print super thin details like this from TPU, it tends to catch on the previous layers and push it around, which gives you a horrible looking print. So I made all the fins joined in the center, but only for the printing process. Once a print was complete, I went in and cut each fin free, and this was the result. I went with Ford AM's 85A TPU for the wheels, and it's very soft with a lot of give. Pretty cool. For the rear armor though, we want something a bit different. The 85A stuff is probably way too soft, so I printed one out of 95A and another out of the 64D TPU. And honestly, I think I like the 64D one more. The fins feel springy with a nice toughness. In fact, the properties remind me a bit of polypropylene, but without any of the annoying hassle that printing with polypropylene actually needs. That just leaves the chassis and the forks. A very large part of combat robot competitiveness is the ground game. You need to get under your opponent if you want to hit them or control the fight. And the forks need to take an absolute beating. So I figured that they're the perfect robot element to put this range of engineering filaments to the test with my very own homebrew impact test jig. This jig lets me swing a hammer into the forks with high repeatability and accuracy. It's loosely based off the Charpy impact test, but instead of trying to create a standardized test, I'm just really interested to see how my robot parts perform in a simulated robot combat impact. To constrain the forks, I 3D printed this chunky support block from Pro 1 PLA, which is a crazy strong PLA blend, which got my attention years ago with its performance when I was testing the static load of 3D printed gears. And with anything destructive, safety goggles are strictly required. And we'll kick things off with Ultrafuse Pro 1 PLA. Despite its strength, this filament is just as easy to print with as regular PLA and has a really clean, almost pearlescent surface finish, and it has really good mechanical properties, so let's see how it goes. Okay, wow, so with the hammer at 22.5 degrees all the way up to 67.5 degrees, this filament held its ground, and you can see almost all of the energy going into the sample is being conserved and reflected back as the hammer bounces back almost as far as it swung. In fact, the fork barely deflects at all, even all the way up to its limit, but boy, was that limit reached. The impact shears the fork clean off, violently sending it flying across the room. So it's clearly incredibly stiff, but when it fails, oh boy will you know about it. Now onto the other end of the spectrum, we have UltraFuse TPU 64D, which is a stiff TPU, but these are still flexible forks. I'm not sure how well these would hold their shape in an impact, so let's find out. I find it so interesting just how different these results are from the Pro 1 PLA. These forks absorb a ton of energy from the hammer hitting them, deflecting in the process. It's not a lot to begin with, but once the hammer is at the near top of its swing, the forks bend so much that the hammer just passes by and actually gets jammed in this awkward position with the forks bent out of shape. Forks like this, I think, would be great against nasty spinners, but when it comes to the ground game, I suspect they won't be as effective as a more rigid material, and they could even get bent or jammed up under the frame if the impact is large enough. Next up is this crazy stuff, UltraFuse PCGF30 from Ford AM's reinforced filament line. This is polycarbonate with a 30% glass fiber fill and has a print temperature range of 280 degrees up to 330 degrees C. As you can imagine, it's got quite good temperature resistance and it's really, really rigid. So I'm actually really curious to see how it performs. Like the Pro 1 PLA, the PCGF30 seems to be really good at reflecting back the energy from the impacts, but unfortunately it still failed with a hammer at 112.5 degrees, which sheared the sample off at its weakest point. Because it's capable of withstanding such high temperatures, I'll definitely be revisiting this material for future parts that need to be rigid and withstand heat, but for my combat robot forks that will get smacked hard by metal weapons, I don't think it's the right choice. Last but certainly not least, we have UltraFuse PA6GF30. This is a glass-filled nylon 6 and it means the business. The filament has this super rough texture and you do need a 0.6mm or larger nozzle to print it or it will clog up. But according to Ford AM's datasheet, it promises very high stiffness and strength with excellent layer adhesion. So let's see if it lives up to expectations. Well, yep, there you have it. I couldn't break them. I put the hammer all the way out to 180 degrees and it still just bounced off like nothing. And it's really important to mention here that I was using the same default print settings for all of these samples. They are not printed more solid or denser or at a different layer height, exactly the same as the other materials. This stuff is just really, really tough. Though I do have a word of warning, this stuff is very abrasive. It needs to be fully dried for printing, and I used a bed adhesion spray for extra security to prevent the prints from failing. And after all of that experimentation, I've chosen my materials for this build. The frame of the robot as well as the rear armor will be printed from the 64D TPU, the wheels will be printed from the very soft 85A TPU, and the forks and top plate are printed from PA6GF30. This is going to be one tough bot. To make the chassis as lightweight as possible but strong in areas that it needed it, I designed in modifier meshes into the file itself, and then within Bamboo Studio, I assigned these modifier meshes a denser infill than the rest of the print. This was especially important for the uprights of the vertical weapon, because I didn't want that area to deform too much on large impacts. But by using modifier meshes, it meant I could make the rest of the print much lighter weight, where it didn't really need that strength. You can use support material with TPU, but I prefer not to, so I designed in these bridging features in the areas that would hold the Malenki Nano, and I especially like how this detail turned out with an overhang that eventually bridges to hold the switch in place. Now all that's left is the tedious job of wiring such a tiny machine. My advice, get yourself a soldering iron with a really fine tip and practice a lot before attempting to wire up something like this, because Some of the components are incredibly delicate and very easy to damage if you don't solder them correctly. And also don't forget, wire fatigue is the #1 killer of combat robots. It's all too easy when you're trying to shove complex parts into a tiny ant-weight frame to move the wires too much and snap them off. And I'll be honest, wiring this little robot took an entire evening to achieve. Take your time, get it right. And with that, I think it's time for a test. This is my worst fear realized. A vertical spinner that cannot self-right is an instant death sentence, and I was so sure that my hub motor would have enough torque to turn itself over when upside down. I've seen a few builders give their verts little sticks out the top to give the blade more of a chance to spin up, so I quickly kludged this one into the design, and no. Because I've made the weapon tooth so aggressive, the motor would need heaps of power to simply turn over, let alone start spooling up. So defeated, I went and whinged to one of my friends about how it couldn't self-right, and he's just like, why don't you just spin it backwards? Spin it backwards. It's so simple. AN32 firmware is super cool in the fact you can actually control sensorless brushless motors bi-directionally. Normally, I'd only consider using that for drive motors, but in this case, it might be just what I need to get this bot back on its wheels when it's flipped over. So, fingers crossed, let's give it a shot. It works. It actually works. And it works really well, especially considering there's a little bit of break in the motor still with the settings, so it actually lands back on its wheels really reliably. I'm so relieved. And as a last minute thing, I designed these stubby forks with additional guards on them printed out of the 64D TPU because there's a few nasty horizontal spinners in the competition, and in that case, I think the wheels might need a little bit of assistance if they're going to stay intact. And with that, the bot is almost done, but we still need a little bit of style. So I asked my in-house designer kindly to draw me up a logo for the bot, and I laser etched it right into the top plate through some paint. I give you Dead Cat Bounce. Coming in at 147 grams, this thing is chunky, and that hub motor looks oh so mean. So I chucked it into the arena for a first real test. First things to note, it sounds amazing. Second thing, it's fast. Honestly, a bit too fast. And third, the gyro is real. Gyroscopic precession is this really weird phenomenon that occurs when a spinning object, like the vertical spinning disc on Dead Cat Bounce, is subject to a force that causes it to tilt or change its orientation. When the robot tries to turn, the spinning mass actually resists that turning force, causing the entire robot to lift up on one wheel in the direction of rotation. That's why gyroscopes and spinning tops are so stable, and why vertical spinners are one of the hardest robots to drive. So with that in mind, why would you make a vertical spinning weapon if there's such a significant trade-off to control? Well, I think it's time for a destructive test. After a bit of wanton destruction, I made sure to hit the walls at full speed for good measure, and yeah, this thing is awesome and seems to be very durable. After months of design work, countless printed prototypes, and a fair few failures, to see it actually work is so satisfying. But can this little robot actually win? Well, after a night of very little sleep, I headed off to our local ant-weight competition to see how Dead Cat Bounce would perform, and this was the result. Enjoy. In the end, Dead Cat Bounce came third, a pretty good result for a brand new robot, and it delivered some absolutely huge hits, but it was very hard to control. Those gear motors are way too fast, and the fin wheels held up to some huge hits, but they did prove challenging to keep pressed onto the gear motor shafts. Because that TPU is so soft, they tended to pull off instead, which is not great because controlling a robot like this with only one wheel is, well...
7, 6, 5, 4, 3, 2...
And the bot's essentially undamaged. The weapon's a bit scuffed up, sure, but it works perfectly. And the frame, the armor, even the forks that took direct hits, they broke a little bit, they didn't rip completely off. That PA6 GF30 from 4am is no joke. I've already got some plans on how to refine the spot, but I'd love to hear your thoughts and comments in the description below, because there will definitely be a part 3 to this build. In fact, I will be competing with Dead Cat Bounce at Robot Royale this December, which will be hosted at the University of New South Wales, and you can compete there too. Thanks for watching, guys. Bye.
I have to go now. My planet needs me.